And our main goal is to explore algorithmic thinking as a lens on the sciences and engineering, as well as to study the laws of computation itself, which is mainly done through semester programs, as well as through occasional one-week workshops. And this workshop is interesting because it's a lead-up to a semester program that's happening next fall. So before we get started, I'll just say a little bit about logistics. So as you saw, there's going to be like coffee and food outside in the breaks, but there's no lunch, so you're welcome to go explore restaurants around and have lunch. If you want to leave your stuff when you go and have lunch, there are some lockers on the other side of the building that you can use. And we do ask that you not bring food in here. So as you can see, this is in great condition after this many years, and that's part of the reason. I want to thank our videographer, Omid Farr, who's over there, if you have any questions about AD stuff related to your talk with us. Okay, and finally, I want to thank our events team, Francis Klingenberger and Ashley Hassan, for doing all the hard work to put this together. So let's give them a round of applause. With that, I'll hand it over to the programmer.
Yeah, hi everyone. Yeah, thanks for coming. Yeah, so very excited for the lineup this week. So as we all know, diffusions is an area that's seen a lot of progress in recent years, and it kind of sits at the intersection of a lot of different disciplines: physics, statistics, TCS, AI for science, robotics. The list goes on. So it's great to see sort of leading experts in all of these areas who will be speaking, and also participating in this workshop. So the organizers, myself, Sinho, Joanne Bruna, Kostas Stochastic, and Arnaud Doucet, we've really tried to put together talk sessions that kind of mix together all these different areas. And the hope is that this workshop will be kind of a seed for interactions across different disciplines. But we want to make this as interactive as possible. So if people have strong opinions on what they want to see featured in the programming for fall 2027, please do drop us a line over email or just over lunch, and we'll be very excited to take your feedback into account. And with that, I think, maybe Sinho, maybe you can mention a bit about our plans for the Wednesday open discussion session.
All right. If you took a look at the schedule, you might have noticed that Wednesday afternoon is free. So we had intended this to be a time for some open discussion. But also, if anyone is interested in organizing some kind of outing, for instance, a hike, please feel free to let one of us know, and then we could maybe set something up. And yeah, maybe I'll just say welcome everyone to the Simons Institute. Thank you everyone for coming to this workshop. And also thank you so much to the Simons Institute and all of the staff who made this process extremely smooth. Okay, so let's begin right away with our first talk by Andrea Montanari, who is an expert in many things, but also has worked on diffusion models recently, and he'll talk to us about some.
But shouldn't it start at 10?
Sorry?
Shouldn't it start at 10 in the schedule? We start early?
Oh, I guess there's still 8 minutes.
Can come up with some jokes for 10 minutes. I'm happy to start early if you want.
I guess. Want to share anything else about the program or what you hope will happen in the discussion on Wednesday?
I guess I can. Well, okay, so maybe just to give a sense for what the program will look like tentatively for the fall. We will have a boot camp at the beginning of the semester, and then 3 one-week workshops. For now, the topics are quite broad, but the first workshop will be on engineering of diffusion models, broadly construed. So really looking into how people in practice interact with these things, how they build them, and this hopefully will be an opportunity for folks in theory to kind of get exposed to questions and opportunities for modeling as a result of this kind of interdisciplinary interaction. The second workshop will be on science of diffusion models, so things related to generalization, phase transitions, all manner of kind of theory-friendly things where there's kind of been this rich interaction between TCS, physics, and ML. And then the third workshop at the end of the program will be on, right now it's titled Diffusions Beyond Generative Modeling. So certainly diffusion models have been used for sampling, but nowadays plenty of other use cases beyond just, let's say unconditional generation. Lots of exciting work in both theory and practice on these kinds of questions. So right now it's quite broad, but we're hoping that in a year these general themes will still be salient. But again, we're hoping to kind of dynamically adapt to this rapidly changing ML landscape. I think we have some dates down. Okay, you have them. Okay, yeah. Yeah, so we have some dates planned for this. That Sino is writing down. Great. Okay. Yeah, and just to say a bit about the Wednesday open discussion, I think for us the biggest question is what are the problems that people in different areas, we're all sort of studying the same mathematical objects at their essence, but we all have different ways of thinking about them and different opinions on what are the problems that truly matter. So hopefully over the course of this let's say this hike that will happen, or at least some kind of social outing, we'll be able to discuss those in a more informal context and get a sense for the lay of the land. Any other thoughts?
No, sounds good to me.
Yeah. All right.
Yeah, since we're all here, might as well start.
Okay, sounds great. All right, Andrea, take it away.
Oh, did you take a picture?
I think it's okay.
It's okay. Shall I start? Yeah, okay, so this is not really about diffusion models, but one reason I'm interested in diffusion models and in diffusions in general is give a way to understand high-dimensional probability distribution. And this is a piece of work in which we use some kind of stochastic dynamics to understand some, as you see, some high-dimensional probability distribution. This is joint work with Michael Wren, who is a student in mathematics at Stanford, and should appear in the next few days on arXiv. And it's at the beginning really of a kind of a research program, so I thought it could be interesting to talk about it here. And as you'll see, this is really very first steps in a sense. So I will be interested in graphs in this talk, and throughout this talk, basically graphs will be matrices, symmetric matrices, okay? So you can think of this as a weighted graph for and vertices, and it's a graph really because we are interested in permutation invariant properties, and H will be a vector, right? So you can think of it as weights on the vertices of this graph, okay? And okay, so I will write subscript 10 every time I want to indicate the number of vertices in this graph, and I will be looking at test graphs. So what is a test graph for me? A test graph. I need to introduce some terminology. So a test graph will be, just another graph, right? That I will denote by WD. And the only difference is that, well, two differences. First of all, there is small n vertices, and second, the edges are non-negative integers, and the weights are also on the vertices are also non-negative integers. Okay, so given a test graph and a graph, we define the homomorphism density Tx in G. So this is 1 over n C of x, where C of x is the number of connected components in X of sum over all the functions, the embeddings of the small graph into the big graph, right? And then I'll take the product over all ij in n, okay, of whatever ai fi fj wij, okay, and then product over I in n h fi di, okay. So this is a very simple, if it's the first time you saw it, and you can think of the example of a simple graph. So these weights, let's say that they are all ones, and let's say that these are zeros or ones, depending whether the graph, the edge is present or not, right? And so in that case, what this is counting, well, it's counting the number of way of embedding the small graph in the big graph in such a way that the edges are preserved, okay? So for instance, X can be a triangle graph, and so this is just counting the number of triangles that are present in G. Okay? And in general, it's counting the number of small subgraph in G. Right, so now there is a definition that is due to Borges, Chase, Kahn, Lovash, 2013, I think, that says the following, is a definition of convergence, and says Gn, okay, a sequence of graphs is left-convergent. Okay, so this is a sequence of graph indexed by the number of vertices, is left-convergence if for any x, so any fixed test graph, Tx Gn, so this is a sequence of real numbers, is convergent. Okay, so this requires that the number of triangle count converges, the number of cliques of size 11 converges, the number of subtree converges, the degree distribution converges, and so on and so forth. Okay, so the limit of this sequence of number must exist and finite. So this is a notion that in a sense generalizes not exactly generalizes, but roughly speaking, yes, local weak convergence. So some of you must be familiar with local weak convergence of graphs. Convergence. Okay, that is due to Benjamini-Schramm and was generalized by Aldous Lyons and Aldous Steele. Okay, so what is local weak convergence? This is perhaps for some of you is more intuitive. Local weak convergence basically looks at, in its basic form, look at a graph and you look at the ball of radius L centered at the vertex I in the graph G. And ball means the neighborhood of depth L in the graph distance, in the usual graph distance. And so we say that Gn converges in the sense of local weak convergence if converges to some G infinity, which is a random rooted tree, a random rooted graph. if for any function phi from the space of random rooted graphs to R, let's say bounded, it has to be also, okay, let's say just bounded, then if I look at, test this function about against the neighborhood of all possible nodes, this converges to the expectation of phi of B. Okay, for any L, B, G infinity, root, comma L. Okay? So here I'm requiring that, every, basically the empirical distribution of the balls in the sequence graph converges to, the distribution of the ball, centered at the root in this infinite tree. Any questions about this definition? So one simple example, you take the three-dimensional grid or the three-dimensional torus, L by L by L, right? And in the sense of local weak convergence, this converges to the infinite Z3, rooted at 0. Okay, so of course, if I look at this definition, the function Tx dot, this is a function on the space of graphs. And is, of course, by definition, by construction, a continuous function. Notice that this definition, I in the definition assume that the number of vertices diverges, but this makes perfect sense also if the number of vertices is constant. It's just a little bit trivial in that case. I mean, it's the usual convergence in that case. Okay? So this is a continuous function because this is exactly the topology that makes this function continuous. And so it makes sense to define L, and in a sense is a local function, right? Because it counts small subgraphs in this big graph. It makes sense to define, it forms the functions, these functions forms an algebra. Multiplication of two of them is also a function like this. It's just taking the union of the graph. It makes sense to define L of G is the completion of this algebra. In the uniform topology. So I'm saying this now in a kind of, abstract way, but what this means is very simple. Take all the triangle counts, subgraph counts. Take all the polynomials that you can form out of them. So number of triangle times number of phi clique plus number of, whatever is your favorite subgraph. So all such polynomials. And then take all the limits, uniform limits, all the functions that can be approximated in sup norm by such polynomials. Okay? So I'll call this the algebra of local functions. Okay, so it's a nice question is which functions belong to this algebra? A general question is which graph functions, graph properties are in L. Okay. Now, I will not answer this question in general, but I look at a special global function, let's say, quote unquote, that is motivated by statistical physics in a sense, and this Ising model. So I have to define to you what are Ising model. Okay, and this is the following probability distribution over sigma in plus minus 1 to the capital N is simply 1 over z of g e to the 1/2 sigma a sigma plus h sigma. Okay, so I just look at I have a matrix, I have a vector, and then I do this thing. Right? Okay, and so this is, and z of g is just the sum of these weights over sigma, and I define the free energy of this Ising model is just defining as f of g is 1 over n log z of g. And the question is this local? Okay. Now this might seem, okay, I have my PhD in physics, so for me it's very natural to ask this question. It might seem why this function and not any other function. Well, one way to motivate this is the following. If you look at z of g, so let's look at the case in which h is 0 and aij are either 0 or beta for some constant beta. So this is a graph, and all non-zero weights are equal. So I claim that z of g counts homomorphism of g into this graph. So here I have beta, and here I have minus beta. Okay? Why? Because if I give you assigning plus or minus 1 of the vertices, it's really a map. Okay? If this is my graph G. An homomorphism, a mapping of the vertices to plus minus 1 is just a mapping of the vertices into the weight here. And if you take the product, I should write this is e to the beta and e to the minus beta. I pick up a weight. Every time two vertices take the same sign, it means that map here, and I take a weight e to the beta, and every time I map to plus minus 1, I take a weight e to the minus beta. Okay? So this is a special case of the question whether do the homomorphism counts of this form Tg in X converge. Okay? So we defined convergence by homomorphism from base graph from test graph to G, but you can ask, does this imply convergence of, in some sense? Here is on an exponential scale of that. Okay? So this question actually was asked already by Borgs, Chase, Kahn, Lovash. I'll mention in a little bit what was their kind of result on this. So the first remark, so is this local? And first remark is that in general, no. Right? And the example is take an antiferromagnet, or what in physics is called an antiferromagnet, which means simply that the Aij are either 0 or minus beta for some beta positive. So either 0 or negative, and let's say that all the Hi are 0. Then it's not hard to see that Z of G is basically the sum over all sigma of e to the 2 beta times the cut induced by sigma in G, right? Times a constant. Okay, so this is a trivial constant. So This is the number of vertices of edges that have endpoints in the different size. And so for large beta, what happens is that the free energy will be dominated by the largest cuts. Okay? So it turns out that this is 2 beta over n times the max cut of G plus order 1, where this order 1 is bounded uniformly. So it's a constant. In fact, it's log 2 at most. Okay? And so the only way that the free energy is local is that max cut is local. But it's very easy to understand that max cut is non-local. It's not in L, right? One example is that you take the random k-regular graph and the random bipartite k-regular graph. The maximum cut of a random k-regular graph is about number of vertices times k over 4, while the bipartite, you can cut all the edges. So it's n times k over 2. And the two graphs converges locally as the same local structure. Okay. So does the question, does the picture make sense? Okay, so now I want to understand. So these examples also tells you that, at least, you see for proving that f of g is non-local, we had to take beta large enough so that we can neglect this term. Right? Of course, if beta is 0, then this is a constant, so it's trivially local. So this perhaps suggests that we have to put some more conditions. Okay, and now I can state the theorem. Okay, so for delta, take delta positive and C positive. So delta is a small constant and C is a large constant. And let G delta C be the set of graphs Gn, such that these two things hold, right? Lambda 1 of an, or lambda max of an minus lambda mean of an is less than 1 minus delta, and then 2 so the maximum entry of any H is bounded, and this is what? This is the operator infinity to infinity norm that is the maximum L1 norm of any row of A. Okay? So the sum of the weights that are, the weighted degree of every vertex. So this must be bounded. Point here is that this constant can be arbitrarily large. It doesn't matter. Then F is local on this subset of graphs. All right? So concretely, it means again that if Gn is left convergent and satisfies one plus 2, then f of Gn converges. So this in particular implies is that if you have any two sequence of graphs that have the same limit, the same left limit, the limit free energy must be the same. Yeah.
In the definition of local functions, why do you have to take the completion of the t's? Why couldn't you just start off by looking at functions induced by these phi's and take the completion of those?
Functions induced by this?
Like, you went through a lot of trouble to define L of g as the completion of the t of the subgraph counts, right?
Right.
So, homomorphisms. Could there not be a more, I mean, a direct definition just in terms of the bounded functions phi used in the definition of Benjamini-Schramm?
Well, because, okay, this is a generalization in which sense? In the sense that I don't know how to make Benjamini-Schramm definition if the graph is dense, right?
Ah, okay.
Now, in the Aldous Steele, they generalized, I think in the Aldous Steele, or it's vice versa, but in one of the Aldous papers, they generalized this by saying, okay, I have a graph, that is defined, and they have a distance function, and that is not the graph distance necessarily, and then I define weak convergence in the same way where this is the ball in that distance, right? But this is now I brought generalizes quote unquote in the sense that this really is a strict generalization of this if the A are bounded. See that here, since they take moments, right, now there can be some trouble.
But mainly it's for dense graphs.
Yeah. Yeah. So for sparse graphs, I could have done exactly what you said, right? Now, okay, so perhaps a couple of remarks. Remark one, this I think in the same paper or in a related paper, they proved something similar statement as convergence of the free energies, but under a stronger condition, under let's say Dobrushin kind condition, which roughly speaking in this context means that A infinity to infinity is smaller than a small constant. I mean small, let's call, I don't remember what they do, but let's say 1/2, something like that, right? While here this constant can be arbitrarily large. And perhaps remark number two, okay, the condition one is in a sense necessary, but condition two looks like it's a proof artifact. So we started this project, being convinced we could prove it without condition two, and we ended up on a small technical thing in the end that we cannot get away. And okay, perhaps some of you will have some ideas, or perhaps, next week I'll ask GPT about it. Okay, let me mention that this theorem has some implication. Okay, so I'll give you two small corollaries that I think are interesting. I didn't know how to prove them before proving this theorem. Okay, so corollary number one is I take Gn to be a k-regular graph. With girth that is bigger than log n square, and hn equals 0, so no magnetic field, and aij equal, so all the weights are equal, so you can think of an edge set Okay, I'll call En the support, of course, of the matrix Gn of the matrix A, and Aij are plus minus beta if Ij is in En and 0 otherwise. So in other words, I'm taking a large k-regular graph with large girth and putting random signs on the vertices. And the consequence of this theorem is that if for beta square root of k minus 1 is less than 1, then limit and to infinity. So this random signing, Ising model with random signs is what's called the spin-glass model. So in this case, we get that the free energy is log 2 plus log cos beta. So before this, I knew how to prove this result for a random regular graph. Now I can de-randomize the graph. Okay. So I still need the signs to be random, but I can de-randomize the graph. And okay, where does this condition come from? It comes, of course, from, the condition on the infinity norm is trivial. It's from the bounded degree. And the spectral condition, well, you have to know about the eigenvalues of this graph, but fortunately, this was worked out by Mohanty et al. 2021, and this builds on top of work of Bogdanov, 2020. And this proves that the largest and smallest eigenvalue are plus or minus 2 square root of k minus 1, the kind of Friedman. Okay, corollary 2. Now let's take again Aij instead to be minus beta 0, H to be 0 again, and let's take a graph converging locally to k regular 3. So this means that it's a bit weaker than that most of the neighborhoods are just trees. Okay, and let's say that, okay, let me call a perp as the projection orthogonal to the all one vector of the matrix A. This matrix has an eigenvalue that is minus beta times k. I'm looking at beta positive. Has an eigenvalue that is minus beta times k. So a priori, to apply my theorem, I would have to take beta less than 1 over k. But I claim that I only need to look at the projection of A orthogonal to this big eigenvector. Now this matrix, so this matrix has eigenvalue that there is a minus beta times k, and then all the other eigenvalue are much smaller. So you, in general, if the graph is an expander or similar, and so that I'll put the condition that lambda max of a perp minus lambda mean of a perp is less than 1 minus delta. And then under this, so this is then limit n to infinity of f of gn is equal to log 2 plus log cos beta. Okay. So somewhat, surprisingly, putting plus minus 1, or unsurprisingly, I don't know, putting plus minus. So plus minus beta means that this spin, this sigma I on neighboring vertices want sometimes to align, sometimes to go in the opposite direction. This means that they want to always go in the opposite direction. This theorem says that it doesn't really matter, surprisingly. Right? So two limits of the free energy are the same. Yeah.
Just checking, so this doesn't work for Wigner
This doesn't work for Wigner matrices, so because of this condition, right? I mean, conjecture is that it should. I would expect that again that condition can be removed, but.
So my question is that here for the limit there is a closed form expression. Does it relate to the theorem? Whenever there is a the convergence is guaranteed, we can compute the closed form?
No, because so first of all, it depends what you come back. So there is a closed form expression. So perhaps I should say what is one way to or what is the way that we prove this theorem, this corollary is we compare. So we have a sequence of deterministic graphs, and we compare with the random regular graph, right? And these have the same local weak limits, right? And for the random regular graph, we can get this closed form expression, right? So this is the way we prove it. Why there is a closed form expression? Well, I think because the tree structure of the local neighborhood is particularly convenient for doing calculation. Will there always be a closed form expression? No. Take again, the k-regular, the d-dimensional grid. This theorem applies, right? Or any other graph that converges to the d-dimension. This theorem applies, right? But now the free energy will be. There is nobody knows of a closed form expression beyond dimension 2, right, for the Ising models.
So, just another question is that can we bound the distance towards the limit?
Can we bound the distance towards limit? So we can bound it. You have to give me, in principle, yes, but I don't think anything. Well, in principle, you could work out to our proof is quite, it gives a construction, but it's not very. Okay, any other questions? So in the last perhaps 15 minutes of this talk, I'll try to give the proof outline, and actually the proof is not hard, so I can explain most of it, apart from the calculations, but I can explain it. Okay, so one way to look at it is that we proceed in 5 steps. So steps 1 is reduction to computing the free energy of log concave measures. Step 2, there is a reduction from computing free energy to average energy. And I'll explain what that means. Step 3, and here were dynamics. There is a reduction from, so this average is average with respect to a Gibbs measure. We go from the Gibbs average to, let me call it Langevin average. So we take an average with respect to Langevin dynamics at some large time. Step 4, we do a time discretization of Langevin. And step 5, we do a polynomial approximation of star. Okay. So now I'll go over it and try to fill all of this. I'll probably fill the first three, and then I'll just wave a little bit my hands about the 4th and 5th. And unfortunately, these are all the these first 4 steps work without condition 2, and the 5th doesn't. Okay, step 1. So what is this? This is this observation that, okay, in physics people, when I learned it, this transformation, they call it the Hubbard-Stratanovich. Transformation. This is when I first learned it in kindergarten. So first of all, without loss of generality, I can assume A positive definite, because I can always shift A by a diagonal matrix by constant times the identity. This, since the sigmas are plus or minus 1, doesn't matter. So this is my partition function. And so now I can write it as, okay, since this is, you can assume that all the eigenvalues of A are in delta 1 minus delta, modulo modifying the delta, and so I'll write this as the integral, well, a constant that depends on n, and I don't want to compute e to the minus 1/2 phi A minus 1 phi sum over sigma e to the h plus phi sigma, that A to the minus 1/2 d phi, okay, where phi is integrated in R capital N, right? And so what this means is basically means that modulo this constant f of g is, now I can, this is separable, so I can sum over sigma, f of g is minus 1 over 2n trace log A plus what, let me call it fv of A minus 1, where f b of b is 1 over n log integral e to the minus 1/2 phi b phi minus sum over I b of hi plus phi I b and phi. Okay, and here b of x is minus log cosh of x. Okay, so it was a kind of kind of remarkable. So notice that b second is always bigger or equal than minus 1, just by calculus. And also by this, b is 1 over a, so lambda I of b are in 1 over 1 minus delta, and some b constant c. Okay, so this means that if I call this e to the minus h, so this was a kind of remarkable result by Bauer-Schmidt. Bodino, perhaps 2021, 2019. that as a consequence, H is strongly convex. Okay, and we will use this. Okay, so now we know that what we want to compute is this free energy of a log concave measure plus trace log. So it's easy to prove that trace log 1 over n is a local function. This is simply follows by taking a polynomial approximation of this over this domain, and then any polynomial can be done by just traces is just counting loops of the graphs. Okay, so this is the first remark. And the second remark is that, okay, now there is one wrinkle here, is that we pass that from a to a minus 1. I claim that if I can prove that if f v of b, f v dot is local over then f, the original f is local. I will not prove this. You need me to believe you that if I have a local approximation of this function, then I can plug in the inverse. I can construct a local approximation of the inverse, again by polynomial approximation of 1 over x, and then stick them together and things work out. So there is a little bit of technical work, but this finishes step first. So now what we are left with is the task of proving that this is local, and I can always shift things around, and so I need to show I can always shift, something proportional to phi square. So it's more convenient to think that this is bigger than 0, and the spectrum is bigger than some delta prime identity. So I need to prove that under this condition, fv is local. Okay, I have 3 minutes to do that. So now step 2. What is step 2? Okay, there is a natural Gibbs measure associated to this log concave thing that is beta phi b phi minus, let's call it v of phi. This I mean the sum of the vi's, okay? So let me call this, let me put times d phi. Let me call only this the Hamiltonian, the energy function. And now I introduce this parameter beta, and the corresponding free energy is f of beta, b comma beta. So what I use is just the simple thermodynamic facts. Okay, I'm interested in this at 1. This bracket denotes mean with respect to that Gibbs measure, d beta. So I can obtain, this is trivially local because it's independent of b and can be computed, in fact. And so I need only to show that this is local. So need prove, or sufficient to prove, that G or B 1 over n h phi beta is local. Okay. Now you need, for integrating over beta, of course, you need some uniformity in beta. In fact, we show that it's well approximated by a polynomial with local coefficients. Okay. So 1 minute, step 3. So step 3 is, OK, now this is still complicated because this means doing integral with respect to this messy Gibbs measure that depends on B on a messy way, right? And so what we do here is we consider Langevin. So we initialize phi 0. So phi 0 is a, OK, so phi t will be a vector in R capital N. We initialize it with nu 0, so with the beta equals 0 temperature. This is independent of B, so it's a local initialization. And then we look at the SDE, the Langevin SDE, which is d phi t. If I write it explicitly, is minus, I think, minus beta b phi t dt minus gradient of b phi t dt plus square root of 2 d wt, where wt is a Wiener process. Now this is, here is where convexity enter. There is a log Sobolev inequality. So this means that the relative entropy of col nu t beta, the distribution of this at times t, versus nu beta, this is the stationary distribution. This is less or equal than nu, OK, let's say, constant times n e to the minus alpha t. This is really the KL divergence at initialization, and this is some positive constant. OK? Now, OK, there is a little bit of work to be done because we want to stop this on time scales of order 1. A priori, this doesn't tell you much unless t becomes at least log n. But in fact, we show that this implies that nu t beta of h phi divided by n minus nu beta of h phi divided by n. So this converges on time of order 1. So it's sufficient. While for the KL distance to equilibrate, to converge to 0, you need to take time of order log n. Turns out that to get the energy to equilibrate, you only need time of order 1. This is, it's not a very difficult lemma, but is non-trivial. OK, and now I'm done my discretized time. So we do Euler discretization with time steps which are of order 1, small but of order 1. And step 5, so you can imagine what is this discretization. We replace this by polynomial. All right, so after any finite number of steps, this will be a polynomial in B, and we are done. Now, the tricky part in this polynomial approximation is that phi is unbounded a priori. So you cannot get uniform approximation over an unbounded domain. So you need to control phi and blah, blah, blah. Okay, and this is where this infinity to infinity assumption enters. I'm done. Thank you.
So to relate this to diffusion models, it would be a natural question to ask whether the score function is local or like equivalently like the posterior mean. So I guess you could take these like Gibbs measures, noisy version, and ask that question. Have you thought anything about this?
Yeah, well, the score function will be the gradient of the Hamiltonian in this case. So, is it? I mean, the score function per se is, if the Hamiltonian is local. I mean, for instance, if this model is trivially local, right? Okay, the score function of the evolution. That's another question, right? Yeah, it's a good question. I don't know. I would imagine so, but. Another question related to I mean, there are many questions related. You could. Okay, here we introduce these dynamics. There are many ways that you could go about doing these proofs, and this worked out, but doesn't mean that. Well, we tried a few alternatives. One alternative, this diffusion is a way to construct explicitly the Gibbs measure. The diffusion process, the denoising diffusion process, is another way to construct explicitly the Gibbs measure, right? So can we use that to prove this theorem or stronger version of this theorem, right? And then, of course, if you go back to the convergence of graph, you want to look at models beyond the Ising model, right?
So my question is whether the proof can helps us to estimate the limit as well.
Well, this so this gives an algorithm, right? In a way. In fact, we don't need even the polynomial approximation to get the algorithm. The algorithm is simply you run Langevin for order 1 time, and then you do this, and then you integrate. Now, this algorithm is not per se particularly new, right? It's just the usual kind of reduction. Now, what is non-trivial here is that, or what is different from what you would do normally in computer science, we run an algorithm. We run this process much less than you would do, right? You run it only for order 1, so this distance is still very large. In fact, the total, I can give you examples I don't know in the Ising model, but in other models I can give you examples in which the total variation will still be 1 and still the energy is close, right? So I don't need to wait until the total variation becomes small, which requires log n time. I only need to wait. And the other thing is that, since I proved that it's local, this gives a local algorithm. So in theory, you can imagine that, algorithmically means each vertex needs only to run something, needs to have knowledge only of a bounded depth neighborhood of every other value in the graph. Okay, thank you.